last time we considered applications of the criteria of failure. Let us consider second example on the application. It is given that a shaft is made up of a ductile material with sigma y 207 MPa, modulus of elasticity 207 GPa and Poisson's ratio 0.25. The shaft transmits a torque 6750 Newton meter. It is subjected to a maximum bending moment 900 Newton meter. Using a factor of safety equal to 2, determine the required shaft diameter. So, the shaft is made up of a steel, and it is indicated that you have to make use of a factor of safety equal to 2 on the yield point, and therefore, if we have to go for solution, we must make use of allowable stress equal to sigma y by factor of safety, and this will give you 207 by 2, that is nothing but 103.5 MPa. Now, let us look into how we go about applying the criteria. Look into the component. If we draw the component schematically here, this is the shaft. It is subjected to twisting moment and also it is subjected to bending moment. You remember that when we apply the bending moment, with this type of bending moment applied on the shaft, you are going to have tensile stresses at the 6 o'clock position and compressive stresses at the 12 o'clock position. Under the action of the twisting moment, you are going to get shear stresses which are going to be maximum around this outer circumference or close to the outer circumference, and therefore, if we consider an element at the 12 o'clock position or 6 o'clock position, that is, these are the elements which are going to be critically loaded. So, now let us consider an element which is just around the or close to the 6 o'clock position. So, I am trying to talk about this element which is here, and it is just close to this position, and if I take this element and develop it, it is shown here. Let us consider that I am sorry, this is x direction and this is y direction. Now, under the action of the bending moment, you are going to have compressive stresses, and under the action of the twisting moment, you are going to get shear stresses. So, shear stresses on the right hand face, it will be directed like that in the same sense as the given torque, and therefore, the shear stresses on this face is going to be like this. Similarly, the complementary shear stresses are going to come up on the top face and also at the bottom face. Now, the stresses therefore are sigma x is equal to, you can get the maximum stress which is given by 32 m by pi d cube, where d is the diameter of the shaft and m is the bending moment. So, this is obtained from the flexure formula, and in this particular case we have clear cut specification that sigma y equal to 0. Note that I have written this sigma x to be negative because it is subjected to compressive stress at the 12 o'clock position there. Similarly, the shear stress which you can obtain from the torsion formula of circular shaft, and this is going to give you 16 T by pi d cube. If we want to consider this material for design, there are two criteria which are applicable here. One is maximum shear stress criterion and the other one is maximum distortion energy density criterion. This is a ductile material, therefore, you have the possibility of considering these two criteria to be applicable. And let us now try to see, if we apply the maximum shear stress criterion, what is the diameter we get. So, first we consider the maximum shear stress criterion. This criterion states that the failure will take place when the maximum shear stress reaches a critical value. Now, the maximum shear stress for this case we have tau max, and it is given, you can calculate from the Mohr circle radius, which is nothing but square root sigma x by 2 whole square plus tau xy square, and if we substitute the value here, then we get this is minus 32 m by pi d cube, and we have a division by 2, that is sigma x by 2 square plus 16 t by pi d cube square. We have been given that bending moment is equal to 900 Newton meter, I beg your pardon, 9000 Newton meter, and torque equal to 6750 Newton meter. So, we have m equal to 9000 Newton meter and T equal to 6750 Newton meter. So, if we make the substitution and we try to write that this tau maximum can have value at the most sigma y by 2 is the shear stress in uniaxial tension, and we have a factor of safety of 2, therefore, it is going to be sigma y by 4. So, therefore, this can have a value equal to sigma y by 2 is the shear stress in uniaxial tension, and the factor of safety of 2 comes here. So, therefore, it is sigma y by 4, and if you try to plug in the value of m and t, you get this thing as 180 into 10 to the power of 6 divided by pi d cube, and these are all in millimeter units, and therefore, what you get from this is that diameter d as 10.34 millimeter, and you can write this value as it is nothing but 1.03.5 by 2, which is 51.75. So, therefore, you have the opportunity of getting d as 10.34 millimeter. We will now consider application of the distortion energy density criterion. According to the distortion energy density criterion, the strain energy density, the distortion energy density at failure should have the value corresponding to the one at the uniaxial tensile, at the yield point in the uniaxial tensile test. So, therefore, if we apply this criterion, SD, strain energy density of distortion, and it is given in terms of the Cartesian components of stresses by 1 by 6 g sigma x square plus sigma y square minus sigma x sigma y plus 3 times tau xy square, and this strain energy density is to be limited by sigma allowable square by 6g. So, it gives us sigma x square plus 3 tau xy square is equal to sigma allowable square, and if you substitute the values, so we have minus 32 m by pi d cube whole square plus 3 times 16 t by pi d cube whole square equal to 103.5 whole square, and this gets simplified to 343.42 into 10 to the power 6 by pi d cube is equal to 103.5, and this gives finally d cube equal to and therefore d equal to 11.78 millimeter. So, it means that we have to use, you see that the two values that we have obtained are 10.34 millimeter and this has given 11.78 millimeter. Therefore, use the larger value. It is good to keep the larger value for safety, and therefore, use D as 11.78 millimeter. So, thus you see how the criteria of failure can be applied for the design calculations. We have considered the theories of failure for materials which are perfectly homogeneous. There is no defect in the material, but in practice you will find that materials are not defects, are not free of defects. You could have materials with cracks. These cracks can be inherent in the material. It can also come up during the service or manufacturing. Therefore, we have situations where we may have to see the safety of a component which is with defects. I would like to emphasize that machine components are made up of materials, they are not all the time free of defects. Think of the casting. If we make a component out of casting, there is a possibility that blowholes will remain in the material which will act as a defect. If we think of manufacturing of a component by welding, then imperfect welding can give rise to some disjoint like a crack in the component, and therefore, there is possibility of defect. So, these are the situations where you find the defect in the material which is coming up from the manufacturing process. Once a machine has been made up of components which are free of any defects and the machine is put into service, you will find that during the service, due to a loading on the component, there can be defect coming up. If a component is subjected to fatigue loading, it may give rise to some defect. If a component is subjected to high temperature, due to the degradation of the material or due to the creep of the material, there can be defect in the material. So, therefore, you find that even if a machine has been put into service with components which are made up of material which are totally free of any defect, after some time these components might develop defects due to degradation. After some usage of the machine, when the machine is still under operation, the question that will be pertinent, under the action of the various loads that act on the component, how do we guarantee the safety? It boils down to asking a question that if there is a defect in the material, how do we ensure the safety of the component, how do we guarantee the safety, how do we assess the safety of the component. This was not possible till about 1950s, but it has been possible to assess the safety of component with defects, and the theory which is useful in this connection is known as theory of brittle failure. I must mention that the brittleness or the ductility of the material is dependent on temperature at which the component is working. It will also depend on if there is some crack like defect in the material. A material like mild steel can be very ductile, but if it is put into use at sub-zero temperature, it may behave like a brittle material. Similarly, a ductile material normally will show ductility, but if a crack is introduced in the material, it will behave or it will feel like a brittle material. So, therefore, the issue which emerges out of all this discussion is that if we have a crack like defect in a component, how do we assess the load capacity, how do we guarantee or how do we assess the safety of the component. So, this has been possible by considering the theory of brittle fracture, and this theory of brittle fracture, it developed along some specific, it developed gradually. So, we would like to consider some of the points which has led to the development of theory of brittle fracture. Now, suppose you think of a component like a plate having an elliptical crack here. The elliptical crack is oriented in the, let us say, XY directions, and the plate is loaded with sigma and its major axis is 2a, and the radius at the end of the major axis is, let us say, rho. For a elliptical geometry, this rho is nothing but, if b is the semi minor axis, then it is nothing but b square by a. So, if the minor axis of the ellipse is 2b, then in that case this radius of curvature at the end of the major axis is b square by a, which is shown to a larger scale here. So, this point let us indicate by A. When the component with this sort of cutout is subjected to loading sigma, it is well known that there will be stress concentration at the point A. So, if this sigma is the external stress, then maximum stress is going to occur at the point A, and therefore, this sigma maximum is equal to sigma A, and it has been calculated by English, and the value is given by sigma into 1 plus 2 square root A by rho. That is the value, and this rho, as I have indicated, this rho is nothing but b square by A. Hence, if we now simplify by putting rho equal to b square by A, then this maximum stress is given by 1 plus 2 A by B. Look at this, that maximum stress is equal to 2 times sigma into 1 plus 2 A by B. Now, if the dimension B is reduced to 0 or the minor axis is reduced to 0, then what we find is that the stress shoots to infinity. So, therefore, what we get now, that this stress sigma y, which is nothing but sigma max at the point A. So, at this point the maximum stress which is acting in the loading direction, it becomes infinity when B is tending to 0. So, therefore, the stress is infinity. Similarly, the strain, this point is subjected to purely tensile loading, and therefore, the strain is also equal to infinity, which is nothing but sigma y by E, that also shoots to infinity. So, if we were to apply the classical theories of failure or classical criteria of failure, which could be based on the maximum principal stress or maximum principal strain, we find that it is not possible, because the magnitude of the maximum stress and the maximum strain shoots to infinity. So, that was the difficulty in applying the classical criteria of failure, and to obviate all these, there was a new way to look at the failure of brittle materials in the presence of crack, and it was propounded by Griffith, and it is known as Griffith theory or energy balance theory. It is also known as theory of unstable crack propagation. Now, let us look into schematically a case of a plate again of uniform thickness, and it is consisting of a crack, sharp crack of dimension 2a. What we are interested in looking for, what will be the condition so that this crack will extend unstably. Alternatively, you think of a situation that you have a plate here which is pulled at this end. It consists of a crack of dimension, let us say A, and what is the condition at which it will extend unstably, or if it extends to a enlarged length a plus delta a, what is the condition that is to be satisfied at the point of onset of extension. Similarly, in this case, if the crack is to extend to dimension, let us say 2 times a plus delta a, what is the condition to be satisfied for the extension of the crack. So, that is the subject which was examined by Griffith, and he considered that this extension phenomena of the crack can be treated like a thermodynamic process, and it can be obtained, the condition for the extension can be obtained from the consideration of energy balance. So, let us consider the second example, that we have the plate with this loading and the crack is of dimension 2a. If you consider for the moment that this particular component is not having any crack in it. So, if you think of a situation that there is no crack in it and it is loaded with stress equal to sigma, then the strain energy, it is a uncracked component, and therefore, the strain energy density at any point is going to be sigma square by 2e, and therefore, the total strain energy stored in the body would be equal to sigma square by 2e multiplied by the volume of the body. So, if you consider the uncracked component, the strain energy stored in the component is going to be nothing but sigma square by 2e into the volume of the component. Now, if we introduce a crack here, because of the crack, you will find that a portion of the material which is just lying above the crack and below the crack is going to be free of any loading, free of any stress and strain. And let us approximate that there is a zone here which is like this. This is the zone, its height is, let us say, it is proportional to the crack dimension a. So, it is beta a, let us say. Similarly, this side also we have a length equal to beta a. So, that is the portion which is going to be load free. If we just consider the thickness of the plate to be equal to T, then in that case the difference in energy between the two cases, we have in the first case without the crack the whole body is available. In the second case we have the body with a portion which is free of any stress and strain, and therefore, the energy in the second case with the crack can be written as the strain energy of the earlier state minus the strain energy which was stored in these two triangular regions. So, if you consider that volume of the triangular region here is V, then we can write that the energy in the second case is going to be equal to U0 minus sigma square by 2e, that is the strain energy density multiplied by 2 times V, that is the energy which is going to be in the second case. Now, we can write the value of this V, and therefore, this difference in energy, if we consider the energy in the second case is going to be reduced. So, therefore, the energy reduction, that reduction in strain energy if we represent by U, that is going to be nothing but U0 minus U0 plus sigma square by 2e into 2v, and therefore, we can write now, let us write here that this U is nothing but U0 minus U1, and therefore, it is nothing but sigma square by 2E multiplied by 2 times volume, and we can write this thing as sigma square by 2E. That volume is nothing but half, this length is 2A and this height is beta A and the thickness is T. So, therefore, this is the volume of the triangular zone, and if you now try to make simplifications, it comes out to be equal to beta sigma square A square into T divided by E. So, therefore, the reduction in strain energy of the body is given by beta sigma square A square into T by E. And in fact, Griffith did exhaustive calculations, and from the exhaustive calculations it was shown that this beta is nothing but equal to pi. You can also see another thing happening, that while the uncracked body is giving rise to a crack, there is breaking of material bonds, and this breaking of material bonds will require some energy, and when we give energy as input to break those bonds, after the bonds are broken, that where does that energy go? That energy gets stored as the surface energy, that energy gets stored at the surfaces. So, I would like to repeat this point again, that when we try to pull the material to break the material bonds, we give some input energy, and as soon as the material bonds are broken, the energy that we have given as input, it gets converted into the surface energy, and therefore, the energy gets stored at the surfaces. And if we consider that the surface energy of the material is a constant, then if we have a crack of dimension 2A in the material, then we have a surface, we have created a surface of area 280 at the top, 280 at the bottom. So, therefore, total area is 480, and therefore, the energy that has got converted into surface energy is given by 480 multiplied by the specific energy, specific surface energy. So, we can write now that the surface energy of the cracked body is nothing but 480 multiplied by gamma s, where gamma s is the specific surface energy. Now, when we try to consider the loading of a component like this component, herein as you are deforming the component, you input strain energy in the body, and as soon as the crack extends, there is creation of new surfaces through the breaking of the bonds, and therefore, this strain energy is getting converted into the surface energy. So, therefore, while the crack propagation is taking place, you have really two forms of energy at play. On the one hand, you have the strain energy, and we have the other form of energy is nothing but surface energy. So, these are the two forms of energy which are going to be involved in the crack propagation process, and as the crack extends, the strain energy of the body is getting reduced. At the same time, the surface energy of the body is getting increased. Therefore, we can consider that there is a conversion of energy from the strain energy to surface energy during the crack propagation process. So, Crack extension is an energy conversion process wherein the strain energy gets converted into surface energy. We can also think of that the strain energy is the source and surface is the sink. And therefore, energy getting transferred from the source to sink during the crack extension process. So, what is the condition for the unstable crack extension? If the energy is getting gradually converted from the surface energy, from the strain energy to surface energy, then what is the condition for the unstable crack extension? So, therefore, there is a rate at which the strain energy is getting released from the body, and at the same time there is a rate at which the energy is getting absorbed at the surfaces. If the energy availability or rate of energy availability is more than the rate of absorption of energy at the surfaces, then the unstable crack extension will take place. So, Griffith stated that the condition for the unstable crack extension is that the rate of strain energy release is greater than equal to the rate of surface energy absorption. So, we can write now the condition for the unstable crack extension, that delta U delta A. So, delta U delta A is the rate of release of strain energy, that should be greater than equal to rate of absorption of surface energy. So, that is delta Ws delta A. So, rate of release of strain energy greater than equal to this rate of absorption of surface energy. This is the condition of unstable crack extension. So, the critical state is therefore is reached when delta W delta A is equal to delta W S delta A. So, critical condition when the crack is going to crack is going to begin to extend is given by this condition, delta W delta A is equal to delta Ws delta A. So, the crack is going to extend when delta W delta A is equal to delta W delta S. So, we can now write the value of delta W delta A. Our U was pi sigma square, U is given by pi sigma square A square into T by E. So, therefore, if we take the derivative, it is going to be twice pi sigma square A T by E, that is delta W delta A, and if that is equal to delta W delta Ws delta A is nothing but 4 T times gamma S. So, this is the condition for the onset of extension. So, this is the onset condition, and therefore, it gives you the loading which will trigger the extension. Therefore, this critical load so critical load sigma critical is given by E into 2 gamma s by pi into a. So, this is a very important relationship. It gives you the critical stress which will trigger the extension of a crack in a material with surface energy capacity equal to gamma s. Herein you see that E is a material property, gamma s is a material property, and therefore, the critical load capacity of a component is related to the crack dimension by this relationship. So, this is the outcome of the Griffith theory, that you can calculate the critical load given the crack dimension in a material with material property gamma s. In general, it is written as sigma critical is equal to E into gamma Gc by pi a. This is Gc is equal to 2 gamma s. This is also a material property and it is known as fracture toughness or fracture resistance of the material. So, the critical stress is given by this one. In fact, Griffith did experiment with glass fibers and he showed that the variation of this critical load with the crack dimension, it varies as expected, it is going to vary like this. So, therefore, it was experimentally verified that this rule is correct. This particular relationship has lot of practical meaning. It gives you for the first time the capability of calculating the load capacity of a component with defect. So, if you are given the value of the loading, if you are given the value of let us say crack dimension A, or it is known, if we consider a component which is with a known crack dimension, then this relationship it gives you what is the load capacity or what is the safe load, it gives you sigma. Let me put it this way, that if we know the crack dimension in the component, then it is possible to calculate the loading which will trigger the crack extension, and therefore, one can ensure safety by keeping the load level below this level. Alternatively, if we know the loading on the component, then it is possible to calculate the crack dimension A which will trigger crack extension or failure of the component. This second approach has given rise to a new consideration for design. It is known as damage tolerance design, damage tolerant design. What it means is that we can calculate how much damage the structure can tolerate, a component can tolerate given the loading and the material property. Before this theory was propounded, it was not possible to assess the safety of components with crack, but after this was known and some more developments took place, the damage tolerant design has come into being and it has been utilized for the aircraft structure design. What is done is that even if the critical component of a aircraft is having a crack in it, one can find out whether the loading acting on the component is still going to lead to safe performance or not. So, that is why this all the airborne structures are examined for damage tolerant design. So, by considering the particular damage in the critical component and taking the loading in the component, one tries to ensure whether the failure is going to take place or not by considering this relationship of the type given by Griffith. One question which can come up, how do we go about determining this fracture resistance of the material? So, let us try to consider how do we get the fracture toughness of the material evaluated experimentally. For that, we consider a specimen of this type and we apply the load here and try to monitor the displacement. If we consider a particular crack size A and if we try to plot the variation of the load with the displacement u, then you will find that since it is elastic material, there is no plastic deformation or nonlinear deformation, we are going to get the variation of load with deflection to be given by this. If you consider a crack of a larger size, let us say A plus delta A, and if we try to plot the load versus deflection, you are going to see now a variation of this type. Here for the same load you are expecting larger deflection because there is a crack of larger size. At the critical level of the load, when the P reaches critical level, you are going to see extension of the crack from length A to A plus delta A. If we calculate the strain energy at any level, suppose we just consider this level of the loading, let us say P, and this is the deflection u, then the strain energy at this point is nothing but half P square by K, where K is the stiffness of this component. If we make use of the compliance, then this is nothing but half P square by C, where C is known as compliance and it is reciprocal of stiffness. If we consider the rate of release of strain energy delta U delta A under a constant load P equal to Pc, then it is going to be given by half, I beg your pardon, this should be, I made a mistake here, it should be half P square into C, and therefore it is going to be half P square delta C delta A, and this is, we have to calculate the value for P equal to Pc. So, this gives you the rate of strain energy release per unit crack extension, and when you have unit crack extension, if the thickness of this specimen is equal to T, then the energy release rate is given by delta U delta A 1 by T delta U delta A P equal to Pc is given by 1 by 2 T P square delta C delta A. If we can draw a curve showing the variation of this compliance for different crack lengths, so we can consider specimens of different crack lengths here, and if we find out the slope, that will give us stiffness, and reciprocal of that will give us compliance. So, we can plot a curve, and this curve will be looking something like this. And if you are trying to do an experiment with a specific crack length, then for that crack length A, you can find out what is going to be the slope of the curve delta C delta A, and hence this strain energy release rate at the point when the crack is extending is given by 1 by 2 T P square delta C delta A, where P equal to P C, that is nothing but the critical strain energy release rate, and this is equal to G C, fracture toughness of the material. At the point of crack extension, the strain energy release rate is critical, and that is nothing but the fracture resistance of the material. So, therefore, in order to determine the value of this fracture resistance of a material, we can do experiment like this. We can take a specimen of a particular geometry, and then we introduce a crack of certain dimension, and we do the testing by applying some load and try to find out what is the load at which the crack is going to extend, and making use of this formula we can find out what is the critical strain energy release rate. So, before you can do that, you must have the information available about the variation of compliance of this specimen with crack length, and when you have got this P C, you take the crack length, that is the starting crack length. For that crack length you find out from this curve delta C delta A, and you have already got from the experiment the value of P C, and from this relationship you can find out what is the critical strain energy release rate, and which is nothing but the fracture resistance of the material. In fact, experiment is done along this line to find out the fracture resistance of the material. So, therefore, what we have done over the last couple of lectures, we have tried to consider the theories of failures of materials which are homogeneous, and we have considered the theories, 5 theories. One is based on the maximum principal stress, then the second one was based on the maximum shear stress, then we have considered the maximum principal strain criterion, then we have considered 2 criterion which are based on energy density. The first one was based on the maximum strain energy density, and the second one was based on the maximum distortion energy density. We have shown that these criteria are not equally applicable to all the materials. The ductile material are obeyed mostly by the maximum shear stress criterion and the maximum distortion energy density criterion, and for the brittle materials the other three criteria are applicable. We have also illustrated the usefulness of these criteria by considering design exercises. Then we have considered if the material is consisting of a defect like a crack, then how do we go about assessing the load capacity of such component or of component made up of such material. In that connection, we have talked about the energy balance criterion, that is due to Griffith, and we have shown that the condition for the unstable crack extension is going to be rate of strain energy release rate must be greater than equal to the rate of absorption of surface energy. Thereby, we have been able to calculate the load capacity of a component with a given crack size, and the same relationship can be useful for calculating the damage that can be tolerated for a given level of loading on the component. Lastly, we have tried to consider how this fracture toughness of the material can be measured experimentally.